are there any questions? Anything you'd like to talk about? Well, 6 minutes or 3 minutes, depending on what your time we're carrying. All right. So let's start then. So today we're going to talk about fundamentals, host, addressing, router, and routing. Sometimes I get the feeling that people confuse these two concepts. So what about fundamentals about IP? We want a network service to be independent of the lower layers. That is not just applying to the network layer, but actually applies to all layers. You want the upper level to be not caring what's found below it. It becomes more handy. If you want to do something, you want to do that, and you don't care what's underneath it. The layer below you, or the one that the API you're interacting with, will handle whatever comes underneath. You don't care. I usually have analogies, but I don't have a good analogy there. Perhaps the following: if you go to a coffee shop and order a coffee or tea, you don't care how the coffee or tea is made, as long as it tastes good. Okay? So we want the network layer, or any layer, but network in this case, to be agnostic or what comes below it. In the same way, the upper level should be shielded from whatever is below or inside of the network level. The transport level should not have to care about topology and ports, etc., etc. We want to shield that as much as possible. Separations of concern. Remember the layer cake? This is one of the effects of it. we want to have an addressing plan that is, ideally, it should be intuitive and available everywhere. But if it's not, it should at least be done in such a way that we have some kind of addressing plan that is uniform or enables us to communicate on a network level. That is, for instance, the reason why we cannot really use the Ethernet addresses as network addresses. Technically we could, but there will be some issues with that. But we want a numbering plan, and we need to make that available to somehow to other entities, primarily the upper layers, and transport layer being one. We can have a connectionless network layer, and we can have a connection-oriented layer. IP is connectionless. And at this point, can someone give me an example of a connection-oriented network level protocol? What? What layer does TCP reside on? And where is transport relative to network? Above it. So TCP is a connection-oriented protocol, but the network level in IP isn't. So a connection-oriented network protocol. What? ARP. That's on layer 2.5. ARP. Layer 2.5. No. If you mean ARP in the sense of address resolution protocol, no. Perhaps the old classic ATM would be considered to be it to some extent, but it's not really. In some way it is, some way it isn't. But try to find one. So, what is a host? From an IP perspective. My definition of a host from an IP perspective is that it is a device with at least one layer 3 address, or with one or more layer 3 endpoints, i.e. IP addresses. I would add that endpoint has to be public in some way, because you can create an entity that has an IP endpoint, but that's just localhost 127.0.0.1. Technically, yes, it is an IP endpoint, but I would not really consider it to be a host. But it is a host, but not really a host because no one else can communicate with it. But it's a host, but it's not. It's not a networked host, but it's a host. Examples. To the left, I think you're seeing a Raspberry Pi, which is a small ARM-based device. Then you have the classical one, printer. That could be wireless or wired, we don't know. USB attached, I don't know. As long as it has an IP address, it would be a host. You have a smartphone, and then you have the classical one, a computer that has a wired connection. Over here, that's an ESP 8266 Feather. It's a small microcomputer running just running a small one program. You program it using the Arduino software. There's no wire interface on that, but that is a Wi-Fi interface. And on that you can push on an IP stack. Makes it a host. And this is really not showing here, but that's a bunch of racks with a couple of hundred of computers. Each of them are a host. They have one IP address or multiple, but the moment they have one layer 3 endpoint, it becomes a host. So the point to carry from that is that just because it's a computer doesn't mean it's a host. If you have a computer without any networking, it's not a host. On the other hand, if you have a phone with a Wi-Fi interface, that could be a host. So don't let the physical view of it have any impact on your judgment. Speaking of physical, all of this we can virtualize. And a virtualized entity can also be a host as long as it meets the requirement of it having one or more layer 3 endpoints. It's just to say, it's a host. This is a very simple schematic or reference model of a host. Here's the network layer. We have the service access points, the data link talks to it, and the upper layers talks to it. In the case of TCP or TCP/IP, it's TCP/IP or the transport level protocols that talk to it, or applications that talk directly to IP. Below it, we have Ethernet or whatever data link layer protocol that this particular host happens to use. As remember, we try to shield the upper levels from the lower levels, right? But this is how data flows. Packets or data arrives in the data link, and if we're receiving data, it arrives in the data link, goes into the network layer. The network layer does its thing. We'll talk about that a little bit later. And then either it moves up to transport or discards it, or does whatever it needs to do it. Vice versa, in other direction, information comes from the top, trickles down, transport level, drops into the IP level does its thing, and then moves it out on the appropriate interface, which could be a physical interface. There is nothing more to it. Now, this is the IP header. Remember when we talked about the layer cake, or I mentioned the layer cake, you had payload. When you moved it from the one layer down to the lower layer, you attached a header, right? Or you could put, technically you could put that in where, but you usually associate the payload with a header on that layer where you're working on it. This is the IP header that will be attached in front of the payload that comes from the transport level, right? This is, by the way, this is the IP version 4 header that is made clear here. Now let's talk through this. By the way, just to make it clear, I don't remember this by heart. I don't expect you to either. I expect you to look it up at when you need it. But there are some fundamentals that you should probably know by heart. I would say the first one is that the size of the IP header, a version 4 header, is 20 bytes. This is something you should remember. you can have options. If you have options, you put them after the destination length, and then the header grows. But nominally, it's 20 bytes. The important fields are listed down here. The first nibble, first 4 bits, indicate the version of the packet that you received. And just to be clear here, when you receive this into a host, or if you happen to watch this as it flows across a wire on the network, you're seeing the bits in this order. This is the first bit you see. And then all the way over here, and then this line. And then this line. Like this. So you don't see everything in one chunk. Now, hey, it's packets, right? Remember what I said about layer 2, that we actually receive a complete frame? It's checksum, and if it's incorrect checksum, it's discarded, right? So with that in mind, the IP level, if it gets a packet from the lower level, assuming Ethernet, but it receives a frame from the lower level, it receives the entire frame, or as much as possible that it can get, because we can have fragmentation and stuff, but it will have the entire frame. For simple argument, it is the entire frame, but there can be cases when it's not. So, we get it in this direction. So the first nibble is the version. And there are version 4 and version 6 that are currently in operations. Version 4 should be replaced by version 6. Things are moving along, not as fast as we were hoping, because when I gave this talk early 2000s, I said the same thing. IPv version 4 is being replaced by IPv version 6. And nothing much happened in the last 15 years, but things are moving in this direction. So perhaps when you retire, IPv version 4 is gone. Now, the reason why it hasn't been removed is because their install base is so huge. And it's much simpler to implement IP version 4 compared to version 6. But things are changing. So we have version 4 and version 6. What to remember is that eventually there will become a version 8. But the naming systems or numbering systems of these versions, you don't need to remember precise, but if you see an odd number, that indicates that it's a research protocol. So there's an IP version 5, but you should not see that on the public internet. Or version 7 for that matter. Then we have the IHL, the header length. That indicates how much of the data that you received here is a part of the header, as indicated here. And the length, that's wrong. As you only have 4 bits, it indicates the number of bytes as far as I remember. Or nibbles. But you take that value, multiply by 4, and then you get the number of bytes that are present in the header. Not so important. Usually you're using a system that decodes and shows this to you. A very good example for such a tool for viewing what goes on the network is to use Wireshark. And I strongly recommend you install Wireshark and take a peek at the traffic that leaves your computer. Then you can see what goes on, and Wireshark is pretty good at decoding and showing it to you in a human readable format. Type of service. This was intended to enable us to have differentiated service. IP is what's considered to be a best effort service. If I can't deliver it, I will deliver it. And all the packets are treated equal. The type of service was intended so that you could signal or indicate to the network, hey, this is a very important packet that needs to have perhaps low latency. Then you can tag it up, and then the network, when it reads it, hey, this is a low latency packet. I put that as in a special queue, so I will treat those first before I go to the bulk data. So for instance, if you have voice, possibly some video, these could be tagged like that. Now, as far as I remember, there isn't any standard across the internet how these are supposed to be tagged, and each operator can tag them and do these differently. And if you as a user at the endpoint tags your packet, there's no guarantee that the operator will treat them accordingly, because you don't know what these, because that's just a sequence of binary numbers, right? You don't know what these bits mean. I know one company, a big operator in Europe, when they got the packets from their customers, they actually modified the packets and tagged them with their TOS fields across the network, and when they left their network, they cleared the TOS field again. So it left, because after it leaves their domain, they don't know how the other guys treat it. But they use the TOS field for internal scheduling or internal queuing. The next field, total length. This is how big is this IP datagram in total. That means how many bytes can it be? How big is it? Now, if you see that we have this, by the way, one row here is 32 bits. This here is 16 bits. If you have a value that is comprised out of 16 bits, what is the biggest value we can represent? 2 to the power of 16 minus 1. You don't know that by heart? What? 5? 511? That's what, 9 bits? You're just 60? Yeah, 65,000 something. I have to do a little bit more there. So around 65,000 bytes. So that's the biggest IP datagram you can send. Do you remember how big the big frames you could send on Ethernet?
$48 bytes?
Ethernet?
Yeah, address was 48.
64.
Biggest, that's the smallest. What is the biggest you can send? 1500 bytes. And if you have gigabyte bit, you can send 9,000. But let's say 1500, because that's perhaps the normal. So 65,000, how do you squeeze that into 1500?
Segmentation.
No. But yes. On this level, it's called fragmentation. Hopefully it will be included somewhere in slides. But basically it means we take this 65,000 and then IP real, oh, I got 65,000. Shit. I can only send chunks of 1500. Bummer. Okay, so what it does, it takes this 65,000, chops it up in 1500 bytes, puts the header there, and then indicates, puts a header there, length, and then puts a flag here, fragments. It says more fragments, and then puts an offset. And the offset indicates, I'm running ahead of here. So I take this 65, split it up into chunks of 1500 roughly. I put an IP header on it, says there's more fragments, and then I set an offset according to where in these 65,000 or whatever size I have, where should this chunk of data that I have be placed when you reassemble it. And then I give that to the lower layers, and then ship it away. And then I repeat that for all the fragments I have, and then hopefully it will be correctly reassembled at the other side. Time to live. Time to live specifies how many seconds the packet is allowed to live. And I hope that means now you're telling a bullshit story. Because that is it. It is. Time to live is the number of hops that this packet is allowed to transit before a router who sees this should throw it away. Why do we need a time to live?
Because delay.
No.
Because if there is a problem when sending the packets and it never reaches its destination, you can just turn in the network.
Remember what I said about loops in Ethernet? In Ethernet on layer 2, we spend a lot of resource time resolving loops, preventing loops. IP doesn't have loops from, it shouldn't have loops, no network should have loops. But in the case that, as you pointed out, if I send a packet to a router, like in assignment 1, and that router doesn't know what to do with it, it perhaps have a default router. And that one, so you will send it to that, perhaps, and this guy doesn't know where it is, and then it sends it to another router, and perhaps it goes back to some router in the beginning, and then suddenly you have a packet that goes in a loop. And if you wouldn't have the time to live, this packet would be circling the internet forever. That would be bad. First, the sender will never know that it's gone. Should perhaps handle that somehow differently, but it will consume resources. So when a router receives a packet, it reads the packet, looks at the destination, looks at the time to live, subtracts 1 from the time to live, checks, is this 0 now? If it is, discard the packet and perhaps notify the source unreachable or time to live expired. If it's greater than 0, put the frame into the corresponding interface where it's supposed to be going and let it travel on its way. But the time to live is to prevent the packet to live forever or spend too much time in the network. The initial values for the time to live is set by the source. And depending on what operating system you have, these values can be different. The biggest value you can set is 255, which is a lot of hops. But normally we're talking about 64, 32, or something like this. But if you see a packet that has a very small TTL, you should know that that can have possibly traveled a lot. But that's the point of TTL. Protocol. The point of the protocol field is to inform the transport level, or actually to tell the IP level, the network level, who's the recipient. What transport protocol is the recipient of this packet? IP doesn't care what's inside of the payload, but it kind of needs to know, am I supposed to hand this to a TCP stack, a UDP stack, or whatever transport protocol that is defined there. And here are a couple of these protocols that are defined. Mainly, we're using TCP and UDP, but you also see that we have ICMP, the pings, and we have OSPF and GRE. OSPF is the routing protocol, and GRE is an encapsulation protocol. But there are a bunch of protocols we can use. Then we get to the header checksum. The point with header checksum is to make sure that the packet has not been corrupted in transit. Now, again, recall in the case that you have Ethernet underneath you, if there has been any corruption to the packet or frame in transit, the checksum will fail for the frame and it will discard it. However, if there is a change within a router or an IP level, the Ethernet will not detect that. So, example, you receive a frame, you decode it, you realize it's an IP datagram. The checksum is fine on layer 2, moves it up to IP, decodes it, it's fine, moves it up to an application. The application does something, and for some reason it corrupts something there. It doesn't recalculate the checksum for some reason. It just moves it down back to the stack. A new Ethernet checksum is calculated and then transmitted. Receiving side gets it, does the decode, matches the checksum with its received checksum, moves it up, and then you have a corrupted IP packet moving up. And so in that case, we would not catch it. And then remember that the point here is that IP can be transmitted on other layer 2 technologies that may or may not have error checking. So for that reason, we need to have a checksum, at least on the header, to make sure that the information that we're using to make decisions is not corrupted. This is just a checksum, so we cannot recover from faults. It just, same number, okay, worked. Different number, something is corrupted, throw it away. So there's no forward error correction in this case. After that, we have the source address. A 32-bit address specifying the source, who sent this. And then we have the destination address. Again, 32 bits, whose recipient. And as perhaps if you remember the Ethernet frame, that order is different. In that case, we have the destination all the way up in the top. This is the first thing we're in for, because we can read, followed by source and then the type. So in the Ethernet way, it would be destination, source, and protocol. And there's no length in Ethernet. But here we have version, length, protocol, source, and then destination. And then if we have options, those will be coming next. Questions on this? This is the fundamental. And now we're going to be talking about versions or the details. So, when it comes to addressing, the addressing has two parts. You have a network address and you have a host address. Network ID, host ID. For IP version 4, the network or the address is 32 bits, whereas for version 6, it's 128 bits. So there's a little bit more there. But remember the split, network, host. So an address comprises of two parts, network part and host part. Here are a couple of examples of the way you can write addresses, and there will be more. This is two simple version 4 addresses, and when it comes to the IP version 6 address, it becomes a little bit more complicated. It's 4 times as big, right? Yes, it's 4 times as big. So here's the full address, but you see there's a bunch of zeros inside it. So the first way of simplifying that is to replace consecutive zeros with just 1 and remove initial zeros. If you have a 0 in the middle or at the end, you cannot remove it. Because if you would remove this one, you don't know if it's 37, 370, or 3700, right? You don't only the initial prefix zeros. And then to shorten it even further, you can replace multiple sequences of zeros with just double colons. So then when you decode it, it's going to be 21, blah, blah, blah. Ah, there's something missing here. It's supposed to be 4, add a 0, blah, blah, blah. And then, okay, you don't really know how many double quad zeros are missing here. Jump to the back and start filling in the frame packet address from the back. And then, okay, we're missing 2 32-bit numbers. But computers are good at that. And DNS is even better, right? Subnet mask. The point of the subnet mask is to allow us to split the address into the network part and the host part. The way it's operating is that you take the address, apply an AND with the mask, and that will give you the network ID. If you do the same thing but the negative mask or the inverse mask, you will get the host ID. This here is mainly used by things that are routing, I would say. But it's also possibly used by the host when they have to, if they have multiple paths to choose from, because they need to know which network does this belong to. There are 2 ways of noting the subnet mask. That is the traditional class-based notation. You've used it in vector sizes. 255, 255, 2550. The simpler and more shorter notation is just to use a slash and then the number of bits that belong to the mask, and the mask identifies the network ID. How many bits in this address belong to the network ID? The other bits, of course, belongs to the host ID. Now, as it's a mask, it's a binary mask of 2 binary numbers, there's nothing that technically prevents us from having a mask that is not sequential ones. So you could have a mask that would be 1101. But don't ever do that. So these guys, the dotted, this is by the way called the dotted decimal notation, and this is this class-based or slash-based notation. They are equivalent of each other. You should have no issues reading either of them. I write mainly with the slash-based notation because it's simpler to write. Instead of writing, what is it, 16 characters, I write 3. So, an example. Here we have an address, 192.168.0.1. We have a mask of 255.255.192, equivalent of /26. Here's the address expressed in binary. Here's the mask expressed in binary. If we mask them, and we get these. By the way, wildcard is the inverse of the mask. You see there? But you don't really need to know that. It's just the inverse of mask. So to get the network address, you take this and we end up with that. The only thing you see is that this one was just removed, becomes zeros. 192.168.0.0/26. That's the network address. Now, in that network address, we have 2 specific addresses. I should perhaps mention that before. We have a broadcast address. And the broadcast address is used to reach all the entities on that network. And once upon a time, in their almighty wisdom, the IETF decided the broadcast address is the highest available address in the network. So in this case, the highest available host address would be 111.111. And that happens to become 63. The minimum host available address is .1, because we cannot use 0 because that's the network address. The highest available host address is 62. So in this case, the number of hosts in this network is 62. Crystal clear? Hopefully I have another example of it. I do. So, another example, we're using we have a different address and a different mask, /25 in this case. Okay, the address 65, mask 25, here's the address, here's the mask, that would be the wildcard, inverse of the mask, and the network address would be here. There. There's the, no, actually this one too. Here's the network address. Now, the broadcast address is the highest available host address. Okay? So the last 7 bits indicate that. 25 to 32. The difference is 7, right? Last 7 bits are broadcast address. The lowest host address is .1, the highest is 126. Still pretty understandable, right? I'm just going to point out one thing here. So this address that we had happens to be in the middle of the network, roughly. Now, if this address happened to be 130, what would happen? What would be the network address?
That's 30.
What?
Yes, you.
No. It's going to be 151.130/25. What is the address? What comes after this? 128, right? So that would change. And so the next network come after this, given that it's the same size, will start at 128. It will end at 254. So the network address will be 128. The first available host address is 129. And the last one is 253. Do that exercise for your own understanding to see how that works. Okay. This is again just an explanation. The subnet splits the address into the network part and the host part. The number of bits defined in the subnet specifies where this split is. If you have a large subnet mask, which you usually end up is around here, 24. If you have it in the middle, it's a /16. I think that would classically be called a class B network. But we don't use B class-based network anymore. But they are still around. And then in the class A network, you would have a /8 address. And it's in a class A network, or if you have a /8 mask, you will have 2 to the power of 24 hosts within a network. That's a lot of hosts. Now, let's talk about subnet, forwarding, and gateways. Sometimes I use the word router, sometimes I use the word gateway. In most of the cases, they are interchangeable. They mean the same thing. However, in some cases, a gateway might have more functionalities than a router. For instance, you can have a media gateway that would be doing some kind of, it gets some kind of data in one format, and then a gateway can then transform it into another format and move it away. So potentially, it is all context behavior, dependent. But when I'm in the IP context, router and gateway are in the same thing from my point of view. So in this case, we have a very simple setup. We have a host, and we have a small network with 3 additional devices. This device has the address 192.168.1.12. This is 1.14, and here's the network address 192.168.1.0/24. On this device wants to send a packet first to 192.168.1.14. This device. What happens? Okay. The IP level gets the packet, takes the address, applies the mask. So takes the address, and actually, now just to be, this is a little bit bad example. It goes from the bottom. So it takes the address 1.14, looks at this entry. Okay, the destination is 168.1.0. Okay, they're not the same. Okay, but it has this mask. So I take this 1.14, mask it with the specified mask here. That if I do that, I will end up with a value of 192.168.1.0, right? This is crucial. You see how that happens. And now it compares that result with this. And that's a match. So now it knows, okay, if I want to send this packet, I'm going to send it out on this interface. All right? Okay, so it hands it out to the interface. Hey, please deliver this packet. Goes out here and do a layer 2 thing. Packet arrives here. I'm just going to take a peek at the next slide because I might have a bunch of sequence here. Nope. All right. Stage 2. Now we want to send this packet. Same procedure. 888, mask it with 255.2550. Are those the same? No. Move up. Okay. 888, mask it with 0. And that's 0. So that's a match. And now we're supposed to be sending it to something called gateway 168.1.1. As you see here, that device is not shown in the picture. Now, luckily, it appears in our next picture. So, now, this packet we're supposed to be sending to this device. Okay? So, at that point in time, IP will talk to layer 2 and say, hey, I want to send something to the device that is known as 168.1.1. That is on the layer 2 network here. I need to know that layer 2 address. At the point we ignore a little bit what goes on there, but we're going to get to that later. We get the packet and we send a layer 2 frame, note a layer 2 frame with the IP packet as payload to this entity. Packet moves over to the corresponding device. what happens at the 168.1.1 is basically the same thing. It has a forwarding table that it works its way through. Takes the address, takes the packet, looks at the destination address, looks at the network in its routing table, applies the mask, matches, hits as a match onto that interface, and then works its way through the entire list. And once it's found a match, it ships the frame away or the packet away to that corresponding destination. Okay. But just one thing to mention here. This here, this entry, this is called the gateway of last resort, or the default router. This is the one that catches those packets that haven't received, where you haven't found a match in any of your known paths. So it's gateway of last resort. I don't know what to do with it. I will send it to that guy or that entity because it might know what to do with it. If that entry would not be present here, this guy would kick back and say, network unreachable, because I cannot reach this network. But the way you do it, you say destination 0, and then the gateway that you want to send it to, and a mask of 0. That is how you do it. Now, the order of this forwarding table is critical, because if this entry happened to be before that, the packet would be sent to the gateway before it even has a chance to go to the destination directly. So the order in the forwarding table is crucial. Now, I kind of shimmed away about the translation between network and layer 2. And to do that, we have ARP, the Address Resolution Protocol, ARP. The job of ARP is to translate between layer 3 addresses and layer 2 addresses. Because layer 2 protocols don't know anything about layer 3 addresses. This is an example of an ARP cache that happened to be on, I think it was on my computer a year ago. So what we have, basically, it's a table. It's an IP address. Then the type of layer 2, Ethernet in this case. I might have had a token ring or token bus showing up there. Here's the layer 2 address that would be used there. And C, in this case, means it's cached. I have learned it. You can hard code an address so that, yeah, 10.1.0.42, it is always on this MAC number. You don't need to look it up. When you want to reach that, here's the address to use. And then the last is, what is the interface that this has been detected on? So when the IP layer wants to send a packet to an address, it communicates with our protocol, hey, I want to send a message to 10.1.0.63. If the ARP system has this information, it just, hey, I got it, here's the address. IP takes that, builds its message, and gives it to the layer 2 saying, hey, please send this message to this destination MAC address. So here's the example that I just told you about. but I'm using 142 instead. So IP wants to send this. We walk through the table, we find this one. That's the destination address, puts it there, uses our own source address, but that is done by the layer 2. If you don't specify when you say send a layer 2, it will use whatever MAC address is associated with that interface. The Ethernet will then attach 08 as protocol type IP. And then we have the IP datagram, and here I just included the destination is 10.10.10.42. Out with the packets onto the wire to the desktop. In the case we want to send something to 110.0.46, if we go through this list, which will happen. Well, no. Oh, no match. Then we're in a bit of a problem, right? We don't know where we can reach 10.46. So, what happens then is that we will do a broadcast. The ARP protocol will do a broadcast. Basically, it does a broadcast and says, "Hey, I'm looking for a host or entity that has the IP address of 10.1.0.46. Please," and then you specify the MAC number that wants to know this. This is then broadcasted on the LAN, and this is what kills the data centers if you have a bad layer 2 specification. You broadcast that to all the hosts on that LAN segment. And then if you've done that properly, it will just be on the LAN segment or that particular VLAN. It will not go any further. Hopefully, there will be an entity that sees, hey, I've been assigned, I'm using 10.1.0.46, and it will reply, hey, 10.1.0.46 is at, and then it attaches the MAC number that that was on the interface that discovered the ARP message. That packet travels back because it had the requestee's address as source. Now the host learns it, attaches it to its cache, and then can forward the frame. Correct. So, a router. So a router is a device with 2 or more layer 3 endpoints. So that could be a computer with 2 interfaces, a computer with 1 interface but multiple VLANs. Could be a classical router setup or anything like this, but it has more than 2 interfaces. And, oh, correction. Has more than 2 layer 3 endpoints. This traditionally it was interfaces, but we have to be clear, we're talking layer 3 endpoints. Because you can have 1 interface, you can have 0 interfaces. In the virtual case, if you're running a virtual machine, that machine has virtual interfaces, okay, but there are no physical interfaces. The point being, if you have more than one layer 3 endpoint, a router can move packets from one network to the other. That is the business of the router, moving packets from network 1 to network 2. That's the only thing it should do, or should do. It can do other things as well, like security, filtering, dropping, and stuff like that. But the primary task is to move packets from one network to another. That's it. No magic. Yeah, move packets to or from network XY. Again, an example. In this scenario, this is, by the way, the router that we have, the main gateway router, main router we have in our research lab. It has, what is it? 6 physical interfaces. This is the routing table it has. You can view the routing table in a Linux device using route-n or IP route or something. I'm an old style guy, so I'm using the old commands: if, config, route. You're supposed to use the new commands that are IP. So you learn both of them. This is the routing table. This is the default gateway. See it, recognize it. And here are the other networks. So in this case, you see, if we want to go to the 30 network, we're actually sending it to a different computer, 184.64, which happens to be on this network. So, example again. We receive an IP packet on this interface. Destination 151.73, and the source is 10.4031. By the way, if you're implementing a router, never mind. Yeah. If you're implementing a router and you know which interfaces are edge-bound interfaces, so these are entities that are coming from hosts or endpoints, it might be worthwhile to make sure that you get packets that belong to that network and not some other network, because you do not perhaps want to forward packets for someone else. This network here is just supposed to be seeing packets from the 10.4 network, not from Google or something, right? The router would not care. It just looks at the destination. So, what do we do? Well, we're the router. So we start at the bottom. We take the address 73, which is the destination address we're looking for. We apply the mask. We got 64. Okay. That address matches the network address we have. Okay, that means we're going to push out on Ethernet 0. Now, when we do that, we have found our destination. We found the match. We move the packet there. We do not change the IP packet apart from 2 things. We do 2 modifications to the IP packet. We don't change the source or destination. We just take the packet, move it up, and we make 2 modifications. Any idea what modifications we make?
The time to believe is decreased.
Yep. And? if we change the time to live, what happens to the header? It changes, right?
We need to update the JSON.
So we need to calculate the checksum again. So we decrease the time to live, recalculate the checksum, and then we give it to the layer 2. Hey, deal with it. And that could trigger an ARP and stuff like that. Now, another example. So we're getting in on 184 interface, on the 184 network, Ethernet 4, and the destination is 186.13. Okay? So we start at the bottom. Nope. So 164 is not the same thing as 86, right? Check the next one. Ah, here we have a match. We do have a match, right? Cool. So we push it out on that interface, Ethernet 1. Again, subtract time to live, recalculate the checksum. Push it out. Okay. Now we have another example. Destination is 148.91. And I kind of abbreviated this because we would be going through all of the entries here. No match, no match, no match, no match, all the way up to the top. And then we have a match because 0 equals 0. And in that case, we're supposed to be pushing it out on Ethernet 0, right? So no match, no match, no match, no match, no match. Here's the match. Subtract time to live, recalculate checksum, and push it out. And the difference perhaps between the previous ones is that this is actually going to a specific IP number. So the layer 2 protocol now has to generate a packet that goes to that address, the layer 2 address of that IP number. And do note that the IP numbers that have been used are found on networks. Well, no, we're pushing it out onto an address that is within one of the networks that we are aware of. So in this case, I actually continue the example. All right? So destination 91, source 51, through gateway 65. Go into this, we find the address, layer 2 address for the 65, translates that, and then we push that into an Ethernet frame, or layer 2 frame, Ethernet in this case, where the destination matches the layer 2 address of the 65. We use our source, type 8000, hexadecimal 0800, and IP package is unchanged with the exception of time to live and checks. Packet goes away on Ethernet 0. That is how routing works. Or I should perhaps call it forwarding. Because I haven't talked how this table is being updated. If it's updated. In my host, it's not updated. It's static. Now, here we have a difference between data plane and control plane, routing and forwarding. Some people will say what I've just described is forwarding. We've just forwarded the packets. And I agree. Sometimes you still use the word routing. But routing is perhaps a device has a forwarding table. This is the table that is used for moving packets from one interface to another, from one network to another. That's it. Routing describes that as well as the procedures and approaches that are used to update the forwarding table. If you have small networks that are not changing that much, static routing works like a charm. If you have networks or environments where you have changes, static networking sucks. To help with that, we have routing protocols. Now, we can separate this into a control plane and a data plane. The control plane is the environment or the path, the parts where we run our routing algorithms or our smart things that does its thing and then updates the forwarding table when there's something new to do or update or do something with the forwarding tables. But the idea is that is seen to be working in the control plane. We're controlling the data plane. Whereas the data plane, the main job of the data plane is to shuffle packets or do a specific job as fast as it possibly can do it. Nothing else. This comes straight out of the Crusoe and Rose book, by the way. So, for details, look into Crusoe and Rose. Not details, it's rather high level, but it's good enough. So, the aim of a routing protocol is to, well, depending on how your network is, it could be to find possible paths. It could be to find good paths. It could be finding paths that are fast, cheap, whatever you want to, whatever weight you want to put at it. But it's basically used to identify or create topologies, not topologies, but ways of moving packets around in interconnected networks. That's the point of routing protocols. And here is one way of representing a network. So these are routers, and then you have links between these routers. And each link has, for instance, a weight in this case. And so technically, the router X can communicate with router Z either through W and then Z, or through Y and then Z. So there are multiple paths we can choose from going here to Z. If this is broken, we could go like this. Still cheaper or delay or whatever than this, but there's a bunch of paths or different ways. And depending on what routing protocol you use, they are doing these different with different aims. You can optimize for delay, you can optimize for latency, redundancies, and changes. But graphs are usually a way of abstracting networks or descriptions of networks. Costs. So I'm not going to go into details on this. You can read this in the book. Basically, when you do your routing algorithms, you will have a cost associated with the link or the path or something, and then depending on what you're optimizing against, this may or may not have an impact of how you do it. This is a little bit more important, worthwhile mentioning. We have 4 categories or 2 different viewpoints. We can have routing algorithms that are global or decentralized. In a global scenario, you have something that collects all the information about the network state, does its magic, and then pushes out the result. So that's a global viewpoint. The good thing with that is that you can end up with an optimized solution that works the best. The drawback is that a couple of them. First of all, if the network is changing frequently, you will have a lag or a delay between you collecting the information, running your optimization algorithm, and pushing out the result. And when you push out the result, the network might have changed. So that will possibly be an issue. The other part is that in the case that this central entity is removed or crashes or destroyed, there's no one pulling information, doing the optimization, and the devices have to fend for themselves. The opposite of that is the decentralized information. This is where each router has only its viewpoint. I am here, I can talk to that, and that entity, and based on that information I can exchange with these 3 guys or 3 entities. I build my viewpoint, my view, and start to forward packets accordingly. The latter one is more, I'm not going to say resilient. Well, it is resilient in the sense that it doesn't depend on some central entity, and potentially it can manage, if this guy disappears or is destroyed, it can still hopefully find different paths. Drawback, it will take more time. So we have global or decentralized. The other way you can see it, or the other viewpoint, is static versus dynamic. Static, basically, we mean we set our routes in the beginning and then we don't change it. Or we change it so infrequently that it's something we can do only when needed. Dynamic, okay, we change these routes more periodically or when they are needed. Then there's unknown triggers when that is needed. Dynamic versus static. I'm not going to go through the link state routing algorithm. I'm not going to go through the distance vector algorithm. I'm not going to do the comparison of them. We're going to talk about scaling.
Is it important that we learn them?
What?
Digital and the other one, is it important that we learn them?
It's important that you understand the principles of. It's important to understand the principle of link state and distance vector, because those are fundamentals, I would say. But then there are implementations of that. Remember, standards, protocols, technology protocol standards. And I would say that these here are theories, implementations, protocols and standards. So knowing the theory, you will then see these in different implementations of protocols at different layers. Right? So know the theory and principles of them. Again, more applied, I focus on more practical parts. So, in the book they talk about ideal drivers. And that, in a reality, we kind of touched it already. We have these masks. And the point with the masks is to some extent to limit the number of entries in our forwarding table. Because we want to be able to, when we get a packet, the time it takes us to go through the entire list of entries in our routing table will determine how fast that packet moves out on the other side. And we want to make sure that that is as small as possible. If we have a large routing table or forwarding table, that will take time. Similar, if you have the routing protocol to build an optimized routing entry, the more networks or hosts you need to track, the more complicated your optimization will become. So we want to keep it as small as possible. So possibly we can have millions or billions of destinations. We cannot store that in our tables. And then we have this external administrative autonomy. I want to run my network. You should not have anything to say how I run my network. I run my routing super duper algorithm. Yours sucks. Yeah, no, mine is the best, yours sucks. It doesn't matter. We shouldn't care about, we don't want to getting into that. In my domain that I'm managing, I can run my protocol. I can configure it how I want and how it's suitable in my domain. You configure how it's suitable in your domain. We don't need to care. We shouldn't care. Now, I almost messed this up. However, on the internet scale, the internet is a network of networks. So within my network, I can run my protocol. When in yours, you run your protocol. But in between our networks, we need to have some kind of agreement. So for that reason, the routing protocols are divided into two different, they're divided into two different types of protocols. The intra AS routing protocols, and AS stands for autonomous systems. Domains could be one word, but in internet language, it's autonomous systems. This is routing among hosts within the same autonomous domain. So for instance, BTH is an AS, Within BGH, we do our own routing. Here we have, so in this case, it's not required. Yeah, you kind of want to have one way of doing it within your autonomous system. Use one protocol, and that's the one you're using. Of course, you can mix it, but you are doing it on your own. But they are routing the traffic within your autonomous system. Outside, we have inter-AS routing. This is routing between. So when the packet leaves me, I need to have a routing protocol that I talk to everybody else that I know with. We can come to an agreement, okay, how do we exchange routes? So I guess I serve these guys, these networks, and you tell, I serve these guys, and then we can exchange information like that. But then we have a standard routing protocol, or a couple of routing protocols that are defined up here between autonomous systems. And the most predominant there is BGP. So here's an example. So here we have 3 AS. There are a bunch of routers in each of them. And in this case, the router 1D has its forwarding table. It's being fed both by the inter-AS routing protocol as well as the intra-routing protocol. We need the internal routing protocol to determine where do we send the packets when they're supposed to be inside our AS, and we need the other one to handle when the packets are leaving our autonomous system. Inter-AS task. Okay. So, sample again. A router here gets a packet that's destined somewhere else. Where should it go? We need that information in our forwarding table. And let's say that it actually will go to a network outside of these. So this AS has to inform both of these other ASs. Yeah, if you want to go to any of these networks, I'm capable of forwarding these packets. Similar, this guy needs to tell that. So they need to exchange this information. So if this router says, I'm going to over there, okay, I can send it to this guy. We'll send it to this guy, pass through. So we need to do that exchange. Now, if you build your network, you will have specific routers that are doing the autonomous routing, the external routing. You don't want to transit that traffic across your network more than you need to, because transit traffic just sucks up your resources and doesn't give you much gain, perhaps. So this is perhaps a reasonable setup. You have redundancy, so in case that this wire goes down, you can still go that way. But you do not want to have something that trickles down here and then goes all the way up. The intra-AS are known as interior gateway protocols. Examples of the internal routing protocols are RIP, OSPF, and IGRP. I would strongly recommend that you understand RIP and OSPF, because you might be using them in one of the packet tracers. You should learn how it works. OSPF, open shortest path, is basically a link state algorithm with all of the benefits and drawbacks of link states. Now, you can use an OSPF-like protocol between ISS or AS. The IS routing protocol is nearly identical to this, but it's not exactly. It's a link state protocol. You can read this too. It's here is an example how you can do it. Take your exercise 1. And now your subnet or your network is actually comprised of more than one router. But together they form an area or something. And then you have one of these routers are connected to a backbone. Now this router here is aware of the networks that its node has down here, similar to this guy. And then when you connect these guys up and you use OSPF, you can have these exchange information. So this guy becomes aware of these networks, similar over here. And this way, when you add a router to your backbone with the corresponding networks, all of the other routers becomes aware of it after a while. It takes some time, but they learn it. The example that I had here, it was a 2-tier level. You had a local area where you run one OSPF, and then you have one that runs in this area. So these guys down here exchange information. This is aggregated up on this guy, and then it exchanges that information with these guys. It doesn't exchange all the inner details. It tells, hey, you can reach these networks through me. It doesn't say you can reach that network through that router, because these guys, how do I reach that router? It doesn't help me. How many pages do we have left? So, okay, BGP, how many, or anybody worked with BGP? This is the border gateway protocol. This is the main protocol that is used between autonomous systems on the internet. Compared to the OSPF and those protocols, you have an entirely different set of conditions that govern how routing is done. For instance, in BGP, if I'm a transit or if I have an autonomous system where there's a transit capability, I might be very happy to say I can transit all the traffic to all the other networks. And then everybody will send their traffic to me. It will flow through my packet, my network, and I will ship it out to the whoever can handle it from my point of view. If I am a person of lesser morals, I might be looking at all of those packets. And I will see everything that goes on, right? If for instance, if I'm a competitor, let's take the following example. If I am Volvo, perhaps I'm not so keen to route my traffic through Mercedes, right? So in BGP, you have different constraints when it comes to where or how you push your traffic around. Read on BGP in books. I'm not going to go through it. There's more information in the books. But you need to know how BGP works in principle. Just like I would say you need to know how OSPF works in principle. All right? Oh, lots of animations. Once upon a time I had time doing animations. End. Okay, so questions. Any questions online? No. Now, as I kind of briefed, or actually, I went through the slides on routing rather quickly on the routing protocols. It's not an exam in this class on the routing protocols, but you need to know them. You need to know the link state distance vector algorithm protocols. You need to know roughly you need to know the principles of how OSPF works. You need to know the principles of BGP, how it works, what's the difference between them. And then from a practical perspective, you will be using OSPF in Packet Tracer, you will be using RIP in Packet Tracer to set up networks that have dynamic routing. And you will be using these algorithms. So if you know how the algorithms work, I think you will have a higher probability of succeeding. You are now also knowing the interactions between layer 2 and layer 3. You've been informed about the difference between forwarding and routing. And you know the principles of how things are going to go. When a packet is generated on the IP level, or it goes into the IP, it checks the forwarding table, moves down to layer 2, checks the ARP cache, perhaps there's a lookup, then it moves out to the layer 2 network, either directly to the end device or to a gateway. In the case it goes to a gateway, the gateway reads the packet, does the same thing in the forwarding table, determines the output, subtracts 1 from TTL, recalculates checksum, moves it out onto the next layer 2 network. Easy peasy. You know how the subnet mask works. The difference between an address is divided into network and host ID. You know there's a network address, there's a broadcast address, there's a minimum and maximum host IDs. Wow, you know everything by now. These are the fundamentals. Absolute fundamentals. This is where the magic happens. This is where packets are forwarded. This is IP. This is the thing that ties internet together. Okay. Any questions?
When is the deadline for exercise submission?
As far as I know, there is no exercise submission. I'm planning on doing a submission for it, just to make sure that you actually worked on it. Because if you don't work on it, 3 weeks from now, you're going to start doing workshops. And then at the end of the workshop, there is a submission at that week. And if you're not being able to do it by then, so now you have training. So train, train, and train. Should I have a submission for the exercises? Yes or no? I can have it. I kind of know who works on the exercises anyway. I know who was present in the exercise. And when we get to the workshop and I get the question, how do I do this in Packet Tracer? What do you think I will answer? Well, we did that in exercise 1. I was not there. Oh, yes, I noticed. More questions? These are 3 really intense weeks. We passed 1. There will be 2 more intense weeks coming. So make use of that time. Do not postpone. Read the books. There's a lot of pages in the books. If you are unfamiliar or uncomfortable with what we talked about today, or yes, read the IP parts in Cruiser Row. Read that. If you're not comfortable with it, read it. You must know it. Read a few chapters in the Cipher book that explains switching and link aggregation and those things we talked about. Read the Limoncelli book. It talks about some really good knowledge. I'm not talking about the things that the Limoncelli book is bringing up, but you need some of that information for the workshops. More questions or any other question? All right. So I will see you on Monday, but before I go, before Tuesday, when the next exercise starts, try to do the exercise before the exercise. So when you get to the exercise, you have already tried it and you can ask questions about it. Tuesday, you're going to install Linux. That means that you need to have a virtual machine, you need to have a computer, you need to have something that can run a virtual machine, and you need to have the media that is required for installing the virtual machine. There is a, I think, self-study part in the class about virtual computing. Perhaps take a peek at that. And look at the exercise and do your preparation and try to do it before you come. Actually, not try, do it before you come for the exercise. So you can ask questions because you will have questions. Okay. No other questions? All right. Have a nice weekend.